In Florida, the standard pool enclosure is viewed as a simple barrier, a mesh screen meant to keep mosquitoes and debris away from the water. These structures actually function as active microclimate management systems, regulating the physical and chemical conditions of the aquatic environment. This regulation is necessary for any pool built within the geographic corridor stretching from coastal Naples to inland Orlando. This map shows why the region is so difficult to manage. The corridor faces a convergence of extreme UV radiation, high-velocity wind events, and constant biological loading from local flora. Operating an open pool here requires near-constant chemical intervention and mechanical maintenance to prevent the water from turning toxic. To survive these conditions, engineers build systems that solve overlapping physical, chemical, and biological threats from the ground up. The stabilization of the pool environment begins at the concrete foundation. The most frequent cause of total structural failure in these enclosures is not hurricane-force winds. It is localized electrochemistry. This threat is known as galvanic corrosion, or electrolysis. This diagram shows the mechanism. When an aluminum frame, the anode, makes direct contact with a steel fastener, the cathode, inside wet concrete, it creates a battery. This electrical circuit causes the aluminum frame to rapidly oxidize and break down at the point of contact. Engineers utilize marine-grade stainless steel fasteners to provide the pull-out strength needed for high winds. To stop the electrolysis, they use a dielectric insulator, like the Nylo-Tec system, which encases the steel fastener in a glass-reinforced nylon sleeve. The nylon sleeve physically separates the two metals, breaking the electrical circuit and stopping galvanic corrosion. Isolating these metals at the foundation ensures the entire superstructure remains firmly anchored during Category 5 hurricanes decades later. Above the anchors, the focus shifts to the engineering of the skeletal frame. Modern enclosures rely on 6006 series aluminum alloys for their specific balance of tensile strength and natural corrosion resistance. While standard components use 6063 T6 aluminum, the massive roof beams shown here require 6005 T5 alloy to prevent the structure from bending under extreme wind pressures. The placement of these alloys is governed by the aerodynamic standards of the Florida Building Code and ASCE 722. This map illustrates the different requirements for different zones. Inland regions are built for 115 to 140 mile-per-hour gusts, while coastal corridors most withstand 175 mile-per-hour marine winds. These building standards acknowledge that raw material strength is only one part of surviving a catastrophic high-velocity wind event. To protect the core aluminum skeleton during a hurricane, building codes require the inclusion of intentional failure points. This is governed by Section 4501.17 of the Florida Building Code, which establishes the sacrificial panel mandate. As shown in this diagram, homeowners are required to remove or cut specific screen panels when wind speeds are expected to exceed 75 miles per hour. Removing the mesh allows air to flow through the structure, dropping the aerodynamic drag coefficient to near zero. With the mesh removed, hurricane-force winds bypass the primary aluminum beams rather than pushing against them like a sail. By sacrificing the screen panels, the survival of the permanent structural skeleton is guaranteed. The final layer of defense is the biomechanical screen mesh. In Florida, open water faces constant photochemical degradation from the sun. The data is stark. An unstabilized pool loses 90% of its free chlorine in just 2 hours due to solar radiation. Homeowners typically try to counteract this loss by adding cyanuric acid, or CYA, to the water. This creates a chemical cycle where high CYA levels lower the water's oxidation potential, making the remaining chlorine sluggish and ineffective. This sluggish state is what allows chlorine-resistant yellow and black algae to bloom, eventually requiring massive chemical shop treatments to clear. The enclosure provides a mechanical solution to this cycle by acting as an architectural UV filter for the entire body of water. By blocking up to 68% of incoming UV rays, the mesh halts chlorine photolysis and maintains the chemical stability of the pool. The mesh acts as the primary chemical regulator for the system, stabilizing the water quality by limiting solar exposure. The efficacy of this shield depends on aperture density, the number of microscopic openings per square inch. This comparison shows the difference between the standard 18 by 14 mesh and the 20 by 20 no-seam mesh, which is engineered to block smaller insects. High-tensile American fiberglass uses core yarns that outlast cheaper imported alternatives, which often contain crushed rock fillers that become brittle and tear within a few years. Owners of open Florida pools pay an invisible debris tax caused by the lack of this protective layer. As itemized here, the costs of excess chemicals, increased labor, and premature equipment failure result in an annual loss of $3,260 to over $6,200. Over a 10-year horizon, the financial drain of operating an unscreened pool in this environment can reach $65,000. The investment in an engineered enclosure stops this financial drain by stabilizing the aquatic environment